All right, example 3, the definite integral. All right, it's time for us to get to what is the exact area. Enough of this estimating and being off. Let's talk about what the exact area is. Well, in mathematics, we call this symbol right here an integral. And what the integral is going to calculate is between the two bounds, or the interval a to b, it'll calculate the area under the curve of f of x, or if f of x were negative, the area between the curve and the x-axis. That's what's always going to happen. It's the area between the curve represented by f of x and the x-axis. Now, I'll talk later about what dx represents. So how mathematically is it calculated? Well, honestly, what happens is this. If you think through what we were just doing earlier, we were looking at the right Riemann sums, which is basically adding these blocks together, and we did the left Riemann sums, and we averaged them out to get a more accurate picture. But that's what we were looking at. We were adding up these different sums. Well, it's going to take the same idea of multiplying the function times the width, where the change of x is the width. Now, we have width of 1 here, and what's going to happen is this limit is going to say, let's make this change of x get smaller and smaller. So instead of us having the bounds subtract by each other, let's divide that, kind of like we did in example 1, by a number that's approaching infinity, which makes the width of these rectangles get smaller and smaller. And so here's a visual to show you what happened. Here's the right Riemann sum. And what's going to happen is I am going to find the area as I shrink this down. And so let me show you visually. I'm going to come over here to my slider. And what I'm going to do is I have created here a list that's going to represent all of these blocks. And what I'm going to do is I'm going to start shrinking the width. Now, as I shrink the width here, you can see that my rectangles start getting closer and closer to the curve. So right now you'd still say that, well, it's an overestimate. There's more blocks outside the curve and every part underneath is covered. So this is an overestimate. Well, as I start getting this be smaller and smaller, you'll start seeing that the overestimate actually starts decreasing. This is not very much of an overestimate anymore. You can see how closely this is coming. And so the idea is this: if we were able to calculate all these rectangles, we'll have a better idea what the area is. That'll be really accurate. Well, what if I keep going further and further? You can start to see this is going to be a really accurate representation. I'll go all the way to there. How similar are these two areas? Well, when you look at them, it doesn't look like much of an overestimate at all. The problem is, how do we calculate this? And I'm not going to get into the algebra today. I'll do the algebra next class of how we can walk through this. What I'm going to show you today is just how to use the calculator to calculate that sum. So how do we calculate the sum here, the sum of all those millions of rectangles? Honestly, I made, let's see here, that's 1,000 rectangles per every unit. There's 4 units. So there's 4,000 rectangles in here. That's what it is right now. Isn't that crazy? 4,000 rectangles. If I wanted to 0.1, if my math is right, that would be 400 rectangles fitting in there. It's extremely small, so small you can't even see them all. So what is that area going to be? Well, what I would do here is I would say int, which gives you the integral symbol, or what you can do also is you can go from your Desmos calculator, hit functions, miscellaneous, and it's right there at the bottom left-hand corner. It's the integral. We're looking from 0 to 4 of the function f of x, which you could type in f of x if you wanted to, like this, dx. And like I said, I'll talk about that dx next class. And this is the exact area, 25.33. But if you don't want to type in f of x, in case you don't have everything typed in, the equation was x squared plus 1. It was just like number 2. Example 3 is the same equation from that we had on example 2. And you see the exact area is 25.3 units squared. 25.3 repeating units squared. Now remember how when we came to example 2c, we estimated that it was 26 units squared, so we were still a little bit over, but this is the exact answer here using the integral. Now, you can just type this part into the calculator and come up with an exact answer. Do not forget the dx. Make sure you type it in just like that, and you should get your answer accordingly. Pause the video if you need more time.